So good morning and welcome to everyone for the 22nd My Webinar, and thanks for making the time. Yeah, so today's topic will be TiDB architecture in a nutshell. So here we will discuss about the basic components with respect to the TiDB architecture and what it means to us. Okay, so this is a small intro about me. Already Divya gave a detailed intro. So I'm one among the TiDB certified professional. I'm a MySQL DBA and a AWS certified database specialty as well. Okay, so this is about Mydbops service, what we provide. So we are into this business for around 6+ years. We majorly provide consulting and managed services on the top open source services, MySQL, Mongo, and Postgres, and TiDB is on the way. Before that, this will be the agenda. It's almost a new database. We'll discuss a small introduction about TiDB and its architecture and how this sharding principle works, and also some small details about how the production workload should be and what are the things you should check before moving on to the production. Okay. So before moving on, what is TiDB? So TiDB, as you all know, TiDB is an open source distributed SQL database by PingCap. So what is the full form of TiDB? Ti stands for titanium, which is a metal resisting the corrosion, corrosive metal. So titanium plus DB. So that is a full form of TiDB. And TiDB, in a sense, it is scalable in both the ways. I would say that both horizontally and vertically. So horizontally, it supports a native inbuilt sharding, and vertically, obviously, you can upscale and downscale your instance on the fly. And also, TiDB supports on-the-fly addition of nodes as well as the removal of node for the horizontal scalability too. And TiDB is an HTAP database. As I said, that HTAP is nothing but a hybrid transactional and analytical database. That is, it supports both transactional workload as well as the analytical workload. And it is a major important thing is it is not a new database that you have to create your own connectors, those things. It is compatible it is wire compatible with MySQL protocol. That is whatever the application or the JDBC connector which are already using, right? It is directly compatible with MySQL protocol, and to specifically it is 5.7. And this is, as I said, as it is horizontally scalable, it is highly available by default and also a fault tolerant database. Let's see how it does this high availability as well as the fault tolerance. Okay. Next, coming back to before moving on to the architecture, we'll see about what are the scalability issues which we foresee with respect to MySQL. So MySQL is a great database and it is into the business for and the top open source database for websites and e-commerce, wherever we are using, right? It is very scalable, but there are limitations with respect to MySQL, wherein you can hit a single node limitation. Means you cannot keep on scaling your instance. There is a limit, right? So you might hit a hardware limit, such as a CPU bottleneck or an IOPS limitation is possible. That is one limitation, and other is it does not support native sharding. Means inbuilt sharding is not available with MySQL. That means the horizontal scalability is very limited. Means you can have replicas, and even with the clusters like Percon XDB cluster or a GR cluster, it will be a shared nothing architecture. The data will be redundant and it will fail out, but it's not using the commodity hardware. That means you cannot shard on the fly. And also there are third-party tools such as Vitis. They support sharding, but that needs an extra effort from the application team or the DevOps team or the infra team. Okay, so these are the scalability issues what we see here with respect to MySQL, and we'll see in upcoming slides how it is solved by TiDB. So TiDB architecture. The TiDB architecture is designed upon a design principle such as it is completely loosely coupled. Means it is layered. For example, TiDB cluster, it will be a separate layer, that is a SQL layer, and it has a separate set of servers, and TiKV, which is our storage layer for the persistency, and it is built on top of RocksDB. And TiFlash, it's our analytical and columnar store. It is built with respect to the ClickHouse. Okay, it is a lot of engineering work has been gone through that. And last is an important component, that is a placement driver, which is an orchestrator or the component that handles everything. That means orchestrate everything within the cluster. So as I said, this is the basic architecture when it comes to TiDB. So the PD cluster sits on top of and controls the entire cluster, and it is responsible for allocating the TSO and data location, that is the metadata information where the actual data resides. And TiDB is your SQL layer in which your application connects. You can add n number of TiDB servers, that is a SQL interface layer, and TiKV and TiFlash. These are our storage clusters. They interact with the TiDB using a distributed SQL API and KV, that is a relational to key value pair transformational API. Okay, let's discuss each blocks or each layers in detail in the coming slides. So first, as we said, it's a TiDB, which is our SQL interface. This TiDB is completely stateless, does not store any of the data. You can add nodes to have the increased concurrency with respect to connections and authentication. They're responsible for handling your connection. And also on top of the TiDB, that is a SQL layer, you can also have a balancer to manage the connections. TiDB, that is SQL interface, is responsible for parsing and compiling the incoming queries and distributing among the TiKV nodes to retrieve the data and send it back to the client. So this is the functionality of SQL interface. As I said, the data which is stored onto the disk, that is a TiKV or the TiFlash, they have the key value combination. The data which is being sent back will be in a relational format. So those conversions is also handled by the SQL interface, that is TiDB. Okay, and also it has a module to manage the online DDL execution. It's online, the column addition indexing is online with respect to TiDB, and garbage collection, cleaning the old and obsolete data, and catchy table. Catchy table is a new feature which is being introduced in TiDB 6.0. With for example, you have a you have a configuration table that is which is less frequently updated and it is frequently read, right? Those tables can be read, catched into this buffer. The maximum size of this catchy table is 64 MB as of now. Okay. Now let's move on to the next component, that is our storage layer. So the TiKV. TiKV is our transactional storage responsible for storing our OLTP and serving the OLTP traffics. So this is completely stateful and has a persistent storage with RocksDB. As you're aware, RocksDB is built on top of LSM3, and this is a RocksDB is a production ready and fail-proof DB, which is being used in Facebook, and many large companies use them. And also even a lot of DBs are coming on top of this RocksDB. This RocksDB forms the basis of storage for our TiDB2. And TiKV is responsible for the distributed storage and a transactional support. Transactional support, TiKV supports a dual commit, two-phase commit, and also the transaction manager. You can see this is our block diagram for TiKV. So TiKV has a KV API, which is used to interact with the SQL layer for incoming data as well as sending back to the data. Co-processor is responsible for having the condition pushdowns. For example, this is a single TiKV instance. In a typical cluster, there will be a multiple TiKV nodes. Minimum of 3 nodes is recommended to have a cluster and a HA features. So each node will have a co-processor. Co-processor is responsible for doing the transaction. For example, the data within it and distributing the processor. That its processor is the processing power is split among the TiKV nodes. The transaction node is responsible for handling the two-phase commit as well as the locking concurrencies with respect to the data access. MVCC is all your own, it's multi-version concurrency control. TiKV supports a snapshot level isolation, and also TiDB is completely ACID compliance. Okay, so Raft, KV, and RocksDB, they will see in the future slide how they provide the HA and as well as the data splits and etc. etc. Okay, thank you. Next, we'll move on to the data storage layer. So within a TiKV, the data is being stored as regions. Okay, so region is nothing but a smaller chunk of data. The chunk size is 96 MB. Okay, so this is the 96 MB can't be changed. This the 96 MB is the size of a single region. So you can see here region 1 and region 2. So wherein the region 1 has the values from 1 to 3 and the region 2 has 3, 4, 5. So each region will have a starting point and an end point. So starting meta value and a closing values. Okay, this region is replicated to multiple nodes within a TiKV, okay, forming a Raft group. Okay, so each region will have a, this is how the data is being replicated between the TiKV nodes and provide a HA, high availability, with respect to the data, as well as a fault tolerant one. Okay, so the regions are automatically balanced. This balancing is maintained by the PD, that is our placement driver, which is the brain. We'll see in the next slide. And each region, right, for example, this region 1, key 1, 2, 3 will have a leader as well as subsequent followers. Subsequent followers, the 2 followers by default. And these followers will be responsible for replicating the data. And in case of a failures, these followers will be promoted as a leaders or future leaders. Leader is responsible for the both read and the write operations. Okay. And as I said, PD maintains this region information, actually where this region 1 exists in TiKV node 1, node 2, or node 3. This metadata information is completely managed by the placement driver or the PD. Okay, let's see detail about PD. Sorry, before that, here is a Raft group as well as a region segregation. So you can see here, I have 4 TiKV nodes, 1, 2, 3, 4, wherein I have the regions. I have 5 regions in total. Region 1 handles the data between A to E, and region 2 F to J, and region K, and subsequently the region split happens. Okay, so you can see here region 4 is being replicated from node 1, 2, and 4. Okay, these 3 forms a Raft group. They are connected, they form a Raft group. Okay. This is a single Raft group. Multiple Raft group forms a multi-Raft design. In this way, the data is being replicated and distributed among the available TiKV nodes. Even when there is a high concurrency is maintained, the data distribution, the leader will also be distributed among the TiKV nodes, so that we completely harness our hardware capacity, which is being totally allocated. Okay, so this is the region and Raft allocation, and how the multi-Raft design and the HA and fault tolerance is achieved with respect to TiDB cluster. Okay. So now let's see about the placement driver. The placement driver is I would say, as a brain of the TiDB cluster. This is the only component in the cluster that has a global view, or the God's eye view of the cluster. So the PD driver is responsible for the data placement, that is the region placement, the region splits. For example, when a region grows beyond 96 MB, the region split happens. And also when there's a region shrinks, right, for example, due to a data deletion or a truncation, the data shrinks. So that data merge is also handled by this placement driver. And also load balancing sense, for example, there might be a region which is being kept as hot, means the data access and the frequent updation might happen with respect to a particular region. When this region is hot, and also this particular TiKV node, when they have a group of hot regions, that node might be overused, or it might be under a load pressure. So that is being completely monitored by the placement driver, and they can switch the leader role to the available, the least used TiKV nodes, wherein by distributing the load also. Okay, and placement driver, another important feature of placement driver is allocating a transaction ID for all the incoming transaction, thereby achieving the avoiding the conflict, and also a distributed transaction. And the major and the first foremost work of the placement driver is to allocate a global transaction ID, that is a TSO, for all the incoming transaction. On top of this TSO, we have built this distributed transaction. The distributed transaction and transformation is possible only because of this TSO. So this major activity is done by the placement driver. And as I said, it does the scheduling by collecting the cluster info. That means it monitors the clusters continuously and schedules the region split, region merge, and load balancing, these activities. And PD by itself is a cluster. That means it comes by default with a 3 node, and it works in a Raft group maintained by etcd protocol. So this should be highly available. When there is a node failure, automatically the leader election happens and PD will be up and running immediately. Okay. So next comes our TiFlash. So TiFlash, as I said, it is built on top of ClickHouse for the analytical, and this is a columnar storage, and this asynchronously from the TiKV node with minimal or near to zero disruption, I would say. And there is a feature called with the TiDB, that is our SQL layer. There's a feature called intelligent engine selection. That means when you have both TiKV and TiFlash in the same cluster, when there is an incoming query, which needs to use the TiFlash, this engine selection automatically redirects these queries to the TiFlash. And this TiFlash is optimized for aggregations, join, and a full table scan, usually for the analytical workload. And this TiFlash is optimized for parallel processing and not for the concurrent read. Means high concurrency cannot be handled by this TiFlash. And this TiFlash is an optional module. That means even without a TiFlash, TiDB cluster can function. So next, we'll see about this is a detailed architecture. So we have again, I'm just a recap. So our SQL layer, that is a TiDB, handles the incoming connections, connection poolings, everything is maintained by the SQL layer. And we have our key value store, that is TiKV node, handling the regions and data. You can see the regions, it's a Raft group, region 4, they're all interconnected. And TiFlash, which is our columnar store, and PD, which sits top of all and monitor and orchestrates the entire cluster. So this is how the architecture is for TiDB. Now, let's see about the inbuilt sharding feature that TiDB provides. Okay. So as I said, TiDB provides a native inbuilt sharding. There is no external or manual intervention is needed to enable this sharding. It is sharded by default. So the first thing is the relational to key value transformation. This is done by the SQL layer. And this sharding works based upon the global key. So what is global key? I'll just explain. Global key is used to uniquely identify a row within a cluster, not within a table or database. Within a cluster, within the entire cluster, global ID is used to uniquely identify a row on which the distribution happens. What is a global key? Global key is a combination of primary key plus the table ID. So the table ID is generated by TiDB itself. And there are two cases here for an integer-based primary key and a non-integer-based primary key. For example, if a table has roll number as a primary key, that primary key is taken by the TiDB and it's combined with the table ID, generated table ID, and forms a global key. For a non-primary key tables like varchar or string value, some other values, what it does is TiDB itself generates a row ID, and combining that row ID with the generated table ID, it forms a global key, and based on that, data is being distributed among the TiKV nodes. Okay, let's see with an example. So the first is our normal relational data. So that is consists of 5 columns: number, name, and birthday, cell phone number, and score. And number is our primary key, so which is uniquely identify a row within a table. So now in the next step means TiDB adds a table ID, that is T24 as a table ID, and this 3 dot represent, these two represents our key, and the values after the dot represents a value. So they form a key and they combine together form a value. Okay, so this is a key value transformation and key value transformation, and you can see T24R1 is a value which is used to uniquely identify the row 1 for this particular table. Okay, now again the region split happens. You can see here R1 to R3 is taken as region 1 and it's being distributed. It will have its subsequent leaders as well as the followers, and T2 will again be distributed. Similar way, this happens in a very faster manner. So this is for the explanation, I'm using this screenshots. Okay, so this is how the data sharding happens, and the data is being distributed among the nodes. So now we are just nearing to the last, or how TiDB is readiness for the production. Yes, it's definitely ready and it's to be deployed in the production. You can see Flipkart, Delivery, and Razorpay. So they use TiDB onto their production for the use cases. Means, for example, Flipkart, it's a biggest e-commerce site, and they're able to scale heavily with respect to TiDB. And logistics is Delivery handles the logistics and their products. And Razorpay is again a fintech and payment gateway. So this covers most of the use case. TiDB can be used in any use case. Means it can support any use case. And again, I would say before going on to the production, know the limitations of TiDB. Means there are certain limitations which is currently present with respect to TiDB. I'm just confident enough that will be rectified in the future. For example, a character set support, because some of the character set supports are not supported with respect to TiDB. And test your use case. Do a load testing and a POC how it begins, and then move on to the production. I think we are almost done. And yes, I'm open for questions.